Hey folks, in today's tutorial I will show you how you can leverage the power of rayshader in R to create some amazing 3D land cover maps. We'll be using the ESRI Living Atlas to get one of the crispest land cover datasets that exists out there, and then we will be using this data to create the 3D land cover map of Bosnia and Herzegovina. Welcome back to R, where we will first of all install and then load the packages we need. The list is going to be this time a bit longer, and the list of the names we need is called libs. The first one we need is the Terra package for working with raster files. The second one is the GISCO-R package for getting the shapefile of Bosnia and Herzegovina, which we'll be creating in this tutorial. The third one is the ESA package, which we will use for working with and modifying this shapefile of Bosnia. Then from the tidyverse, we'll be using dplyr for data wrangling in one of the functions. We're working with colors for the land cover raster, and for fetching them and then assigning to our existing raster, we'll be using ggturn package, which comes in handy for transforming your RGB to hex color values. In this tutorial, the 3D feeling will be provided using the elevation, digital elevation model. And to fetch one, we'll be using elevator package. Now, we are going to be creating the overlay here, which is going to be the land cover. And for that, we will need to save this image as a PNG image. So I'm going to be using also here the PNG library. We'll be converting or creating here a 3D map, which means we are definitely going to be using the rayshader package. And then finally, last but not least, we'll be putting together this 3D map that we render together with the legend explaining what are the land cover classes that we'll be using. And for that purpose, we'll call to rescue magic package. Okay, so once we have this list, we can go ahead and first of all see if these libraries are installed. So I'm here creating an object called installed libraries. And I'm using this list object, and I'm going through the row names of already installed packages. So this is actually going to help me see what are those that are installed, and then if they're not installed, then I need to here write actually if-else statement that is going to help us then install them. So if any of these install libraries equals false, if they're not installed, then I open this curly brackets and I say to R, please install packages, but not all packages, only those from this libs list that are not already among the installed libraries. Okay, and then once we have this basically installed, we simply need to load this into R. And loading into R is quite straightforward. What we need to do here is apply a function library to our list of libs. And the library function in R is used for loading packages into R. Now, after loading these packages, if you get this error message, you can just proceed and ignore it. It is simply about the incompatibility between ggturn and ggplot2, but it doesn't mean that the package is not loaded into the R session. Our next step is to fetch the national boundaries of Bosnia and Herzegovina, and for that purpose, we can use GISCO-R. So I'm going to create here an object called country SF, and I'm going to call GISCO-R, and from GISCO-R, there is a function which is called GISCO get countries. Within this one, you need to define the country that you want. So the safest bet is to take the ISO2 code of the country you're interested in. So for Bosnia and Herzegovina, that's BA. If you're not sure what is the ISO2 code for the country of your interest, you can go ahead and check out the link in the description box, where I'm going to provide a link to the existing ISO2 codes for any country in the world. Then the next argument is that you can optionally specify is the resolution, so how crisp the map is going to be. And I can take here the crispest resolution, which is 1. So I'm here at the ESRI Living Atlas website, where you can see a Sentinel-2 land cover land use data at 10 meters resolution. It's one of the crispest data sets on land cover that currently exists. And if you're interested more about this dataset, you can click here on this info button just next to the title in this viewer. Now, the cool thing about this viewer is that here it shows you all the classes that exist. So there are approximately 9 classes. And it can also show you here, you know, for different years. You can even swipe. So pretty awesome source. Now, for us, what is interesting, we want to get the data for Bosnia and Herzegovina. The way to do that is you click here on this downward looking arrow just below this land cover tab. And this is gonna open you a download view where you can actually click on the tiles that you want. So for Bosnia and Herzegovina, we need two tiles. We need this tile and we need that tile. How do I know that? Well, the good thing about this base layer here is that also shows you country boundaries. So I can definitely see what belongs. So what are the tiles that belong to Bosnia, or what are the tiles where Bosnia belongs to? So what we can do next is either click on the link. So for 2022, this is the data that we want, and then locally download, or we can go ahead and copy the link, which I'm gonna do. So I'm gonna copy the link for this tile and also the second tile as well. And then I'm gonna go into R and I'm gonna tell R to download these rasters to my working directory. Okay, now that you learned about the process of fetching these two URLs, we can go ahead and use them to download the files to our local drive. I'm gonna name these URLs, and these are gonna be part of a list. Now, each of them we also need to declare as strings, and the way to do that in R is simply wrap these quotation marks around them. And of course, you need to put here a comma to delineate each member of the list. All right, now that we have that, we can just write a for loop, which will help us download both files. So for URL in this list URLs, and then we open this curly brackets, and then we use download file from base R. So here we define the URL as every individual URL. The destination file name is going to be simply the base name of this link, and the base name of this every link is basically just the name of the TIFF file. And then finally, for the mode, we'll be using the binary mode for downloading. Let's first make sure that we can enlist those files, that we're working in a proper working directory. So for that purpose, we can use list files from base R. And then over here, we need to first of all say the pathway where the files were downloaded. For me, that's the current working directory where I downloaded them. Then the second one is the pattern. So here we're talking about TIFF files. So I'm gonna provide here TIFF. And then finally, I want the full pathway to these files. All right, so then once actually I run this, we should be able to see here only two TIFF files, okay? So that's exactly the case. We have exactly those two files that we downloaded. Okay, so now we can proceed to the next part, which is loading these files into R. Now, as you load these two raster files into R, you will notice one peculiar thing. They have two different coordinates reference systems. So you might be wrapping your head around this, and how do you go about this? Well, in this tutorial, I will show you how you can deal with this issue, and not only that, but how you can actually then aggregate, crop these raster files, and then finally put them together into a single one and make it ready for plotting. So the first thing that we will do here is declare this list and name it raster files. So that's the first thing, because we will be loading these files into R. That's the first thing. The second thing is I want to choose a coordinates reference system that we will use here for now to, as we crop, of course, those raster files, that we convert them into one single coordinates reference system. And for that purpose, I opted for the general one, which is WH84. So this is actually the string that you should use for reprojecting. Now comes the final part and the biggest part, which is about loading these raster files and cropping them, putting them together. So we will actually here design a for loop. So for every raster in the raster files, we will do the following things. Well, first of all, we need to load them. So we're going to load them using these rasters. So para_rast is the function for loading, and we're going to be loading every raster from the list of rasters. All right, that's the first thing. The second thing is we should transform the country shapefile into the coordinates reference system for each of the rasters as we move them in. So for that purpose, we need to use country SF, but we need to actually transform it. So how are we going to transform it? We're going to transform it in the following way, using st transform. We're just going to put here into the pipe. So st transform. And then for the coordinates reference system, we'll be grabbing the one for each of these raster files that we load. So I'm just going to use here Terra CRS to grab what that is. And then here, rasters. Okay. Okay, that's the first part. Now comes the second part within this loop, and that is cropping the raster files. This makes sure that as the raster file, every raster file is loading into this loop, that the country shapefile gets the same coordinates reference system. This allows us to crop. And I'm going to create here a land cover object and use Terra crop function. So within this Terra crop function, first of all, we use this rasters file, all right? And then second is the country object. But because a country object is in this SF format, we want it to be in the vector format so it can be easily manipulated with Terra. So we're just going to curse it here. Then we're going to add the third argument, which is we want to actually take everything that is inside of the country boundaries. And then the final argument is we're going to declare missing everything that is outside of it. In other words, we're not going to take it. Okay, now these files are at 10 meters resolution. So that's a very high grade resolution, which may result in the end in a very huge mosaic and make our lives very difficult with plotting in the end. So what we can do here, we can go ahead and use Terra aggregate to aggregate, so make the resolution not so high, so lower the resolution. And what I can do here is, for example, I can lower it 5 times, so from 10 meters to 50 meters. But here we need to be careful, and that is because each of our land classes is a specific number. If we just go ahead and aggregate, this will average them. So you might get something like 1.5, 2.5, 3.5. And this is not good because then you actually lost information on your classes. In order for us to preserve information, we need to here specify the function that will be used when aggregating. And one function that we can use here is called modal function or mode, which is going to take the most frequent value without averaging it. So then we will have 1, 3, 4, 5, and whatever class there is. So this is the small trick I wanted to show you. And then the final thing that's at the end of this loop that we want to do is simply project each of these files, this raster files, into that coordinates reference system that we previously defined, which is the WHS84. Okay, and then the final part of this function is to actually save each of these files locally. So now why are we doing this? We're doing this because after we save them, we can then load them into R as a part of a virtual raster layer, which helps us actually put together raster files that might not have the same coordinates extent or the same resolution, and ultimately helping us to have a single raster mosaic in a very easy, straightforward way. So for that reason, we're going to go with Terra write raster here. And then first of all, we need to define the object. So it's this line cover. That's what we want to save. The second one is the name that we're going to use. So here we need to actually construct a name from what we have. We can use the raster name, of course. Then we can add here Bosnia, for example, next to it. And then finally, we need to add that it has a diff extension. The reason why I'm doing this is that I don't want to override the original raster file, okay? That's the reason why. Okay, so now we have this whole thing, and then once we run it, we should be able to see those 2 raster files with this Bosnia extension created. Okay, we're ready now to load these raster files as a single file or as a virtual layer file. So we will here, first of all, declare the list of those files that we want to move in. So again, we're going to be using list files. The pathway is, again, the main working directory where these files reside. Then for the pattern, here we'll be using something different. So remember, we added this extension, Bosnia. So we're going to be using that as a pattern of recognition. And then the last thing will be to provide here the full pathway to those files. All right, so in this case now, if we actually run this thing and then we explore our lists object, we will see exactly 2 of these files that have this Bosnia extension. Okay, so we're going to be using now these 2 files. to create a single virtual layer, which we will then use afterwards. So we can use this, we can call this one land cover VRT. And to get virtual layer, you need to use Terra VRT function. So here we need to pass this list of raster files, which we did here. Then we need to pass the name of this raster file. Let's, for example, call it Bosnia land cover VRT. And then we also need to put here an extension, which is also called VRT. And finally, we can put also here, in case you already did this, override equals true. Now, if you print this newly created virtual raster layer, you will notice that here we have values from 1 to 11. But if you plot this same raster file, it's not going to have those nice original colors that we got from this ESRI dataset. So in this section, I will show you how we can fetch those original colors and then how we can assign them to our virtual layer. So here is what we need to do. First of all, we need to load one sample raster file, and I suggest we take the first raster file from that list of 2 raster files that we had at the beginning. So here's how we're going to do it. I'm going to create an object which is called a rust to symbolize this one, and then I'm going to use Terra rust to load that one. And then I'm going to fetch from that raster file list, I'm going to fetch, for example, the first one. You can also take the second one, doesn't matter. The only reason why we need this object here is to grab those colors. Okay, so now that we have this, the second thing is to grab, of course, those colors and put them into a data frame so that we can work with them. So I'm going to actually call this, for example, raster color table. And then the way to do this is to get the colors, of course, unique colors, using call tab function from Terra. Now this will return a list and we want to have it in a data frame. So for transforming a list into some other object, you need to use do call here and then pass that you want to transform it into a data frame. And then the second argument here will be using, as I said, Terra call tab to fetch the color values from this newly created Rust object. When you print the first few rows of this newly created data frame, you might be actually confused because here we got, for now, of course, 6 values, but you see here values for the red, green, blue, and then the alpha values. So these are RGB, so red, green, blue, RGB values, which are not so much useful for us in R. We would rather have hex values because this is what R actually uses. So in order to turn this into hex values, we are going to call to rescue a ggturn package, which has a function for that. So I'm going to call this object hex code, and this object I'm going to use, as I said, ggturn, and the function from ggturn, which is called RGB to hex. And then we need to pass 3 values here. First one is the red value. So if you remember, from that object, which is called color table, we have actually a raster color table. The red one was actually the second column. The first one was value. So we need here to fetch the second column like this. The second value we need is the green, or G. So that one was the next in line. So that was the third column. I'm just going to put it here. And then the last value that we need in order to get the hex code is blue, denoted here by P. And that one is the next in line, which is the fourth value. All right. So once we actually run this thing, and once we then actually print this hex code, as I will show you now, you will finally see that we got all the possible hex code values here that exist. And yeah, as we saw, up until 11, we actually have some values. Everything else actually denotes the missing values. Now that we have also this hex code values, we can go ahead and assign them to our raster file. In this section, we will be substituting the existing color values in our raster with these color values as you see here. Well, not all of them. The reason why I put these first 11 values is that I wanted to check together with you what are actually the values that we need. And right off the bat, I see that we don't need these black values. They simply mean the lack of data or simply none of these categories. So what we essentially need from this list of 11 is the second, third, We don't need the 4th, so we need the 5th, 6th, we don't need the 7th, and then we need 8th to the end, so up until this 12th. All right, so now that we have this information, we can grab actually only those color values that we need. And I'm going to create here an object called calls. I'm going to then take from this Xcode only so those that we need. So that's why I'm grabbing here the following values. So 2 to 3 as we said. Then we don't, we don't need 4, so we need 5 to 6. And then finally, we don't need 7, so we go from 8 to 12. Okay, so those are the values that we need. Now comes the part where we need to substitute the colors. So to substitute, we need to define what we need to substitute and with what thing we need to substitute. So from to. So from, the first argument is basically these values. Okay, so we need to substitute from, in this case, this is not going to be anymore 2 to 3. 2 is going to become the first member of the new list, and then 3 is going to become the second member of the new list. So we need to also readjust that. So in this case, everything here should be replaced with one number, which is lower. So we say here 1 to 2, then we say here 4 to 5, and then finally 7 to 11. Okay, the next argument is 2. So what are we transforming this to? So here we are transforming to these colors, right? So we are transforming to the colors, but here we need to use again another one from ggturn, which is called colors to RGB. The reason why we're doing this is that we need to pass again to RGB values so that Terra will know what to do with them. So it's simply the reverse of the previous one. So this one is called call to RGB, and again, so this comes from, this comes from the base package, so we don't need ggturn in this case. And then finally, we will need to transpose these values so that they can actually fit into our format. So that's why we are putting here T and wrap around everything. And then one final thing with the land cover here, this data that we will be using, so this land cover VRT, what we will need to do here is simply omit any of the missing values. So we're just going to do this. And then the very last thing is to, of course, to finally substitute the values. So I'm just going to call this land cover Bosnia, and we're going to be using Terra subst function, which is basically just substitute. So first of all, we are passing this value here. Second, we are passing from, so from equals from, not minus but equals. The third argument is 2 equals 2. And finally, the names of this one is going to be names equals to colors themselves. Now, if we want to plot this and we use from Terra plots RGB and then pass to this one land cover Bosnia that we just created, you will be able to see the image with those ESRI Living Atlas colors also now applied to our raster. So the land cover raster will be our overlay, but our base layer is going to be the digital elevation model, and it's going to be extruded. So the first thing we will do now is get the digital elevation model for Bosnia and Herzegovina, and for that we'll be calling elevator once more. I'm going to create an object called elev, and then from elevator we will call get elev raster. So here we need to provide locations that we'll be using for cropping. So we want only the Bosnia boundaries and everything that fits into them. So for the first we're calling country SF. And then here is the level of the zoom, how critical it's going to be. I'm going to go for 9. If your country is bigger, then you should definitely decrease this number. If it's smaller, then you should increase it to get better detail. And finally, we will clip by locations which we actually provided in the first argument. Because we want the land cover layer and the elevation layer to fit each other, to have the same resolution, we'll need to resample one to the extent of the other. And because the elevation layer has a lower resolution, we'll be using it just to make our lives easier. So before we jump into that, I here define the projection, the coordinates reference system that we'll be using. Because Bosnia is a European country, I'm again using this Lambert. If you're working with a non-European country, you can either skip this one or define your own for your country of interest. All right, so now I'm going to create something which is called land cover Bosnia resampled. Basically, it's again going to be a raster file, but this time it's going to be resampled. And I'm going to be using here Terra resample function. Here we need to provide 3 arguments. The first one is what we want to resample. So we want to resample land cover Bosnia. The second argument, called y, is what we're going to use for resampling. So we're going to use this elef, but because here we're working with Terra objects, and this one is a raster object, we need to actually coerce this one into a Terra object. And that's easy. We just need to use a Rust function from the Terra package. The final and the third arguments here is the method which we want to use for resampling, because here we're dealing with discrete measures, so discrete values. We will need to use the near methods. Okay, so we have these things, and this is going to resample, and the final step is, of course, to reproject to this Lambert conical projection. In case you're not using it, you can just skip this part. So now if you run again this plot RGB function from Terra, you should be able to see a map of Bosnia that looks a bit different because we applied this Lambert projection, but all the colors are there in their order. And finally, we will save locally this raster file as a PNG image file, and then we'll load it back into R. So this is exactly what we did in one of the previous tutorials on created 3D forest type maps. So in that case, we will first go ahead and define the name of that image. So basically, it's just going to be land cover Bosnia. Let's call it that way. And remember, you also need here an extension. So in this case, PNG. And then the next one will be to save it. We can use Terra write raster for this. We here need to provide the object that we are saving. So we are saving this one, land cover Bosnia resampled. Then in the second one, we need to actually provide the name that we are going to be using this. So this one, image file. The third argument is basically if we want to override the existing one. So this one is optional, it's not really needed, but in case you've been working on this one and you have already something saved under the same name, you can simply override it. And finally, but very importantly, is we want to also declare those values that are NA values. And in our case, those are going to be all the values that have the RGB value of 255, basically those that are black on the image. Okay, once you actually save this on your local drive, you can load it back into R because we will use it as an overlay. And I'm going to call it just here IMG, which is a shorthand for image. And then I'm going to use PNG package to read this image file. And here you can just pass this image file that we previously created. We're almost ready to render the scene, but before we do that, we also need to make sure that our elevation raster is in the same Lambert conical projection as our overlay, in case you're using, of course, a Lambert projection. And then we also need to make sure that we convert this raster into a matrix so that rayshader can accept it for rendering. And finally, we can also use this reprojected raster to extract the dimensions for a rendered scene. So I'm gonna actually name this newly created object that we will reproject LF_Lambert. And then I'm gonna pass here this LF object. Again, you can skip this part if you're not working with the Lambert projection, if you're not reprojecting. First of all, I need to coerce it into a Terra spatial raster format, and then I can use Terra project and then passing here the name of the coordinates reference system. Once I'm done with that, creating this LF Lambert object, I can create also LMAT, which is just a shorthand for elevation matrix. So here we just need to use from rayshader function called raster to matrix, and then we need to either pass this one if you are reprojecting. If you're not, you can use this one, this LF. Okay, and then the final one is defining the height and the width. Height here, I'm going to use H. So the height is going to be the number of rows of your raster file, whether it's this LF or this LF Lambert, in my case LF Lambert. And then the width denoted by W is going to be the number of your columns, okay, of also your raster, in this case LF Lambert. Now that we have all the components, we can finally write the code that will render the scene upon execution. So we start off from LMAT, passing it into a pipe here, and then we're going to be using a rayshader, and from rayshader we'll be going to using height shade, because we first of all need to define that elevation one. So here we need to define the texture of the elevation, Here I'm actually gonna using color ramp palette to increase the number of values, and I'm gonna be passing here one of the colors that we already have. In specific, it's gonna be color value number 9, which is a gray color. And it's actually shows a rangeland, which is basically the lack of vegetation or very sparse vegetation, which will actually perfectly fit with also the background, which is going to be also very rugged. And then what I'm going to do here is I'm going to, for example, create 256 values, but this is kind of a very random. You can put any number you want. Okay, once we have this, we can add the overlay. So we're again calling rayshader and then add overlay. So here we are adding image, which we previously loaded. And then we need to decide what is going to be the transparency of this one. Well, I would like this one to be non-transparent. So I would like the rugged terrain be visible, of course, in the background, but I would like the land cover to be completely visible. So we see completely the colors. And that's why I'm putting here alpha layer equals 1, which means that it's not going to be transparent at all. It's going to be completely visible. Okay, and then the final part here is to, of course, tell rayshader to plot this scene, and the function for that is plot 3D. So here we need to pass once more this elevation matrix. Then we need to pass how big these spikes are going to be, or how rugged it's going to be. The lower the value, the more rugged. So I'm going to go ahead and define this Z scale with something like 12. Bosnia is quite a rugged country, has mountains, so I don't want to go here with a too low value. I'm going to turn off the solid plane around it. And I was putting this here. I'm going to turn on the shadows. So we do want to have the shadows in the background. Then those shadows should be kind of a very soft, so I'm putting here that the shadow darkness equals 1. The background should definitely be white, but you can also change this one. It doesn't need to be of this specific color. We can also define here the window size of the render scene, and for the window size we can actually pass those two values, which are width and height, in this particular order. I'm dividing here by 10 both because the pixels themselves, they're like around 3000. So maybe I could divide by 5, let's say. It's not too much. But if you're dividing width with 5, you should also divide by height so that you don't end up with a very distorted rendered scene. Some other things that you can also define here are zoom. I'm going to choose zoom, which is 0.5. We're not happy with this. We can also change it later on. And then we can also choose the angle. I'm going to go for 85-degree angle. And finally, I'm not going to tilt the axis of this scene. So I'm just going to choose 0 here. Okay, so you will notice that the render scene is done, but we don't see Bosnia in its entirety. But we can fix that. Luckily, in a rayshader, there is a command which is called a render camera. So over here, we can readjust the zoom or any other things. So in this case, I'm not going to change the degree or also the tiltedness angle. I'm just going to go here for zoom and I'm going to increase a bit. So the previous one was 0.5. I'm going to go for 0.58. And once you run this, you will see that now we can see Bosnia in its entirety. So we can go ahead and write a code that will render the object. Okay, now comes a very exciting part because we are ready to create our high quality image. And first things first, I'm gonna here define the name of the file that we're gonna give to it. And I'm just gonna go for a simple one, let's say land cover Bosnia. Well, maybe like 3D land cover. That's not bad. Okay, and then importantly here, I'm also going to define the file extension, which is going to be PNG. Now we're ready to, again, call to rescue rayshader. Render high quality is the name of the function. So here we need to pass the file name, which we already defined also as file name. Then what else? Well, we want to see definitely the preview of the rendering scene as it goes, including the progress. Then again, I'm going to go here for customize lights. So I'm turning off the system lights here. And we can actually download the HDR file as I used in one of the previous tutorials. But I'm going to put actually this in my GitHub repo so you can directly take this file and just work with it. So for now, I'm just gonna here define the name of that lights. And so here, whenever you're defining actually customize light file, you need to put here this environment light. So in my case, this one is called Air Museum Playground 4K.hdr. And again, I will provide this in the GitHub repo, so you don't need to worry about finding it. We can also decide on the intensity of the lights, which is handled with this intensity N. And here I'm gonna go for one which is more or less like a default one. It's not too strong, it's not too weak. Of course, you can go ahead and play with this and see what works for you best. One also other thing that you can do is you can rotate the existing source of the light. And in this case, I'm gonna rotate it by 90 degrees so that the shadow here comes out somewhere in south or southeast. One thing that I like to turn off here is the interactive option. So I don't want to move the scene as it gets rendered. So I'm actually going to turn off the interactive mode here. I'm going to, for example, turn on the parallel option, which allows me to utilize the multiple CPU cores that I have. And then finally, for the width and the height, what you can do is either take this or you can even like multiply a bit, because in our case, this one, it's not that high number. And also for the heights, if you are multiplying here, you should multiply height with the same coefficients. So in our case, 1.5. So the rendering is completed. You can see a crisp 3D land cover map of Bosnia. Now, the next thing is to add a legend to this so that we can actually understand the colors. And one thing you can notice from this map is that not all of those 9 colors are there. So there are some colors that are actually not there, and there are some colors that are definitely there. So I actually here put again a list of those 9 colors. And one thing that we should definitely present here is the number 1, which is water. Number 2, trees. This one is not really there, but crops are definitely there. So the yellow is there. The built up or the urban areas denoted by red are also there. And then finally, the 5th value, which is there, is this last one, which is basically a rangeland. Okay, so in the next step where we build this legend, we will take into account these 5 values. So water, trees, crops, built up area, and rangeland. And the way to build the legend is again following the lead from that tutorial on creating 3D forest type maps. We're gonna go ahead first and foremost and create here the legend name, which is going to be the name, of course, of that legend file that we're going to be creating. So I'm just going to call it land cover legends, for example. And here again, you need to put the extension of this image, which is going to be PNG. Then, because we're going to go ahead and just save this legend, I'm going to go ahead and call this legend name. Of course, within this PNG base R function, you can also define here width and height, so you can give a much higher resolution to your legend instead of the basic one 480 by 480 pixels. But it's not really needed because later on we'll be using Magic package for increasing the resolution of our legend. And then we can also define one of the parameters, which is the font family, and I'm gonna here go for the mono font family. After we have this, we can write the code which is gonna create the plot. So remember here, we are not interested in anything else but a legend. And the legend in our case are gonna be just rectangles with the color, and then next to them there's gonna be a legend label. So in this case, we're writing here that the plot is null because we're not really creating the plot, we're just grabbing the legend from such a plot. There are a couple of things here that we want to define also, and these are, for example, the X and the Y axis text. So we don't need the Y and X axis text because we're not creating a plot here, so we're just putting here N. Yeah, there are some other things, for example, this one BTY, which also should be N. And then, of course, there are also the labs or labels here for the Y axis, which are going to be empty, and also for the X axis, also XLab, also going to be empty. So once we actually have this, we also need to specify some other things. So what are going to be the limits of our plot? So xlim, it's going to simply go from 0 to 1. doesn't mean much because anyways, we are simply grabbing here the legend. So we're going to assign the same thing also for our y-axis. And then also we want to actually expand a bit each of these so that we capture the legend at its fullest and defining for, again, for both of these axes. Okay, once we have this basically empty or null plots, we add the legend function where we create a legend itself. I would like the legend to be centered, so that's why I'm putting here center. And then I need to define the legend labels. So here I'm opening a list. And then, as we said, we're going in the order of appearance. The first one is water. The second one is trees. Of course, if you're wondering how am I getting these, you can either go back to that ESRI Living Atlas and see, those labels. You can also check in the manual that is offered on the website. So this is where I'm getting this from. These are exactly the names that are also used there. The third one is crops. Then we have the built area. And we said that we're going to wrap up with range length. Of course, in case you want to take all those 9 values and put them on your map into the legend, you're also free to do that, because maybe in your use case, there will be some colors that are going to appear. But for Bosnia, really, these 5 are the values that appear. There's some other things that we can specify here. For example, the shape, which is 15, which basically just denotes a rectangular form. Then here we can also specify the size, how big it's going to be. We can also specify the size of the points, which can be actually a bit smaller, and some other things that actually go here, which are pretty, not so much important. But one of them that is important is, of course, the color. So here is where we want to take only specific colors, as we said before. So we're using that previously created calls list. And then we're grabbing here only specific values. So as I showed you, we're going to grab values from 1 to 2, and then from 4 to 5. Okay, so these are the values. We're not actually grabbing here the range length. I mean, we're kind of grabbing it, but we are going to be adding actually here the range itself. We could add it here as number actually 9. Which is also one of our values. So then we actually have 5 values here, exactly. So we got the 5 values here. That's one thing that we want to have here. And then the second one is the filling. So these were the boundaries of our legend keys, and this is gonna be how we're gonna fill them. So using these same colors. And then we can also define the borders of our legend. For that, maybe we can just take some charcoal gray, and then we can wrap this up by enclosing this whole thing, which is gonna then save this legend locally on our drive under the name that we specified. Finally, you will see the legend with those 5 values that we assigned, and also legend labels. And then the final step is to put together this legend with our plots. And if you remember, we do have some place for the legend in the southwest. This is where we're gonna be putting the legend using magic package. Okay, so the next thing is, first of all, load the images one by one. So the first one we will be loading is that 3D land cover map that we previously saved. So we're going to be using here magic and then image read from it. And we can just use here file name, because this is what we use to save that land cover 3D map. And then we can load my legend here, which that's how I call it. Again, using magic image read. And then again, here we are passing the legend name, which you previously used to save the legend. Okay, so now we have this. The first thing is to scale the legend. So we increase its resolution to fit into the resolution of the image itself. And I'm gonna call this my legend scaled. Okay, so here I'm gonna call magic and then image scale function. And then within this one, I'm also going to call another function, again magic, which is called image background, which is going to decide actually what is going to be also the image background. So I'm calling here the my legend, and I don't want any background, meaning I want the legend to be transparent, so to fit the environment of the image. And then finally here, outside of these brackets, I can define how big my legend in pixels I want to be. So I want to rescale it to 3000 because the image itself is also quite large. And then in the final step, what I will do here, I will put together the 3D map and this legend. And I'm going to call here this one P for basically plots. And to put them together, from Magic we'll be using something which is called image composites. All right, image composites. And then within this image composites, we need to do, first of all, rescaling also of the 3D map. So we're gonna again use from Magic image scale, but now we're passing here this LT image that we loaded. Okay, and then we need to specify how much we're going to scale it. Well, if the legend is going to be 3000, we're just going to scale this one to, for example, 7000 pixels. And then once we rescale this, we can use as a second argument for putting everything together this my legend scale. And then we can choose how are we going to position it. So that's called gravity in this Magic package. So as we said, we want to put it to southwest. And we can also offset it a bit from the southwest by adding here values to its X and Y scale. So increasing here a bit these scales and keeping one also constant. And once this is done, you can actually save the image back, but now this time you will have both the legend and the 3D map. And to save, you can use Magic again and then image write. So image write, in image write, you first of all pass this object, which is called P, and then you pass the name of it. So we can simply call it 3D Bosnia land cover and then legends, just to indicate that it has that. And we can also use the PNG as the file extension. And that's all for today, folks. I hope you enjoyed today's tutorial as much as I did preparing it. If you are interested in replicating today's analysis, I prepared the link to the GitHub repo with the full script in the description box below, so do check it out. I'm really also curious how you take this tutorial on a journey across the world and create some awesome 3D land cover maps for other countries. If you have any questions, comments, or just general feedback, feel free to reach out to me here on YouTube, but also on Instagram and X. Also, if you're new to R and you seek to expand your geospatial and data visualization knowledge in R, I prepared a few cool tutorials for you, so do check them out. See you next time.